Hello and welcome. I'm Andrew Deering, and in this video we will be discussing the pharmacokinetics of intravenous infusions. In this lecture we cover the distribution of drugs and how this relates to the volume of distribution. We will then talk about elimination and clearance, and finally we will run through the concepts of the steady state and talk about context-sensitive half-times. Distribution refers to how the drug is spread throughout the body and is dependent upon the physicochemical properties of the drug as well as organ perfusion. As a concept, it is useful to think of the body in terms of a central compartment comprising the plasma and represented by this cylinder, with access to the effect site represented by the central green cylinder. Following administration of a drug, for our purposes we will consider a lipid or fat-soluble drug, the concentration of the drug rises, and we represent this by an increase in the height of the fluid level within this container. When the drug has been injected and is fully mixed, the height of the fluid column is at its maximum. However, as soon as there is any drug in the central compartment, it will immediately begin to distribute out of the central compartment. It is useful to lump organs together according to those with similar rates of distribution of drugs, and so we first consider the vessel-rich group. This comprises such organs as the liver, kidneys, heart and brain. You will notice that the capacity of the vessel-rich group is somewhat similar to the central compartment and is connected with a large bore pipe, representing the capacity for rapid transfer of drug to this compartment. Next we see that the muscles comprise a larger capacity compartment but with a lesser rate of transfer. And finally, we can consider a third compartment, the vessel-pore group, made up of fat and connective tissues. This is a large capacity compartment but with a narrow bore pipe connecting it to the central compartment, which represents the slow rate of transfer of the drug to this compartment. We will now consider two situations. The first demonstrates what happens after a single bolus of a drug is injected. Initially, the central compartment drug concentration will fall due to the transfer of drug to the vessel-rich group, and then the concentrations of both these compartments will continue to fall due to distribution from them to the muscles and vessel-pore group. Next, we will look at what happens during an infusion. If we give a little bolus of drug and then infuse it at a rate to maintain the plasma concentration, you can see that there is a fairly rapid transfer of drug to the vessel-rich group, but that over time the drug concentrations in the other compartments will continue to rise. If we continue on in this fashion, there will eventually be equilibration of drug concentrations across all compartments. It should be remembered that all these processes, including elimination, occur simultaneously. For the majority of drugs, elimination takes place at a rate proportionate to its concentration, and distribution to and from these peripheral compartments at rates proportional to the concentration gradients. So how does this relate to the volume of distribution? Well, the volume of distribution reflects the way in which the drug is distributed throughout the body and is mathematically described by the amount of drug in the body at any given point in time divided by the plasma concentration at that time. The issue is, of course, knowing the amount of drug in the body. The only time we truly know this is at the time of injection, but at this moment the drug is not evenly distributed, even throughout the plasma. One way this is overcome is to plot a concentration time curve and to then extrapolate back to time zero. This generates a theoretical C0, which can be used in the volume of distribution calculations to allow us to calculate this volume of distribution. And so we now see that the volume of distribution is in fact equal to the initial dose divided by the plasma concentration at time zero. If the initial concentration is very low, this demonstrates that the drug must have distributed into other tissues, and as a consequence we can see that the volume of distribution will be very large. If, however, the initial concentration is higher, that demonstrates that the drug has been constrained to the central compartment, and this might mean that the drug, for example, is highly bound to plasma proteins, or that it's highly lipophobic or hydrophilic, and therefore not likely to transfer into these other compartments. Elimination. Elimination is the process of removal of the drug from the body and encompasses metabolism and excretion. The majority of drugs that we will be considering are eliminated under first-order kinetics. The rate of elimination is proportionate to the concentration of the drug And mathematically, this is defined by the exponential decay equation. You can see that the concentration falls in equal proportion over time, and we can see the useful concept of the half-life here shown in red, the time taken for the process to be 50% complete, or the concentration to fall to 50%. However, we should remember this is not the full story, and we will return to this later on. Clearance. You may, like many others, think that clearance is the rate of elimination of the drug. However, this is not quite correct. It is in fact the volume of plasma cleared of drug per unit time, and the units of clearance are therefore mils per minute. If we come back to this concept of the volume of distribution as one large equally mixed volume, you can see that the clearance can be expressed as a proportion of this. As the drug is cleared from the plasma, shown as this red area, it is now apparent that there will be backfilling of the cleared plasma by the drug available in the rest of the plasma. It is the relative sizes of the clearance compared with the volume of distribution which determines how rapidly the drug concentration will fall. A relatively large clearance compared with a small volume of distribution will result in a rapid fall in drug concentration, whilst a smaller clearance compared with a larger volume of distribution will lead to a slower rate of fall of the drug concentration. So if we now look back at our concentration time graph, we can see that the rate of fall of the concentration is determined by K, the elimination rate constant. And K is numerically the ratio of clearance to volume of distribution. Next we will discuss steady state. Steady state is achieved when the amount of drug delivered is equal to elimination. This occurs rarely in anaesthesia, since for the majority of the time, as the drug is delivered to the central compartment, it is being removed from it by both elimination and distribution. Despite this, it is useful to consider the situation. The amount of drug delivered is the infusion rate set on the pump, with the units of mass of drug per unit time, and the amount of drug removed is that amount of drug held within the cleared volume of plasma, again with the units of mass of drug cleared per unit time. And so that amount of drug is in fact the clearance times by the concentration. And so in summary, we can see that at steady state, the infusion rate is proportional to the plasma concentration. I'd like you to remember this. We will come back to this concept during our morning tutorial. Finally, we're going to talk about context sensitivity. So the question is, why does the concentration of a drug fall when you stop infusing it? Well, it's a combination of distribution and elimination. The balance of importance of these depends upon how long the infusion has been delivered, and as a consequence, how full the peripheral compartments have become. The context-sensitive half-time is the time taken for the concentration of the drug to fall to 50% of where it started. Since this involves both distribution and elimination, it is more complex than just the elimination half-life, which describes the rate of that process alone. In fact, each process, elimination and distribution to each of the compartments, can be described by their own kinetic equations, and the context-sensitive half-time is a combination of all these. And so we consider this graph, which shows the context-sensitive half-times for various drugs after infusion durations shown along the x-axis, up to 9 hours. If we consider fentanyl, we can see that the half-time after a short duration of infusion is quite short, of the order of 5 to 30 minutes, corresponding to a process primarily driven by distribution. However, after a much longer infusion, the half-time increases dramatically, as the peripheral compartments have now become filled with drug, and the drug concentration fall is now driven primarily by elimination, a much slower process. However, when we look at remifentanil, we see a half-time which is low and constant regardless of duration of infusion, and this relates to the lack of accumulation of the drug and the relatively large clearance compared with its volume of distribution. During our tutorial, we will discuss the relevance of this. So in summary, after this lecture we should have some understanding of drug distribution and how this relates to the volume of distribution. We have also covered rates of elimination and the clearance of drugs, and looked at some of the mathematics of these concepts. And finally, we looked at the specific situations of the steady state and the impact of distribution and elimination on drug concentration half-times. Thanks for listening, and I look forward to discussing these concepts in greater detail during our morning tutorial.